Now let's show that the binomial distribution satisfies the AB condition. So let n be binomially distributed with parameters n and p. Now we want to find a q0, a and b such that the AB condition is satisfied. As we did earlier, let's just figure out where to start our recurrence. So q0 is the probability that n is equal to 0, and that is equal to let's look here. That is n choose 0 multiplied by p to the 0 multiplied by 1 minus p to the n minus 0. So this thing is just 1 minus p. One thing here, recall that we have to assume that n is natural and that p lies between 0 and 1. I kind of do it a bit different than the case in the book because they sometimes allow for p to be sorry, 1 minus p to the n here, for p to be exactly 1 or exactly 0, but I don't think we should look at the degenerate cases since they're not that interesting. So we just look at the interesting cases. So find q0, a, and b such that this recurrence holds. Okay, so we want this to hold for all k in the natural numbers. Let us first let k be some number smaller than n. And then we will show that this recurrence holds using the definition. So let's start by that first. So then qk is equal to n choose k multiplied by p to the k multiplied by 1 minus p to the n minus k. I want to express qk in terms of qk minus 1, so I will multiply by qk minus 1 and divide by qk minus 1 at the same time. This gives me n choose k divided by n choose k minus 1, then p to the k divided by p to the k minus 1, so that's just p, then 1 minus p to the n minus k divided by 1 minus p to the n minus k plus 1. So that gives me divided by 1 minus p. If these calculations go a bit too fast, you can just try to do them yourself on a piece of paper. Okay, and then I have qk minus 1. Now I plug in the definition of binomial coefficient to continue my uh, calculations. So this is n multiplied by n minus 1 and so on until n minus k plus 1 divided by k factorial, and then I divide by n choose k minus 1. So I have k minus 1 factorial here, and just exactly, almost exactly the same down here, except that now I have to have k minus 1 terms, which means that I only multiply all the way down to n minus k plus 2. Okay, and then I have p divided by 1 minus p multiplied by qk minus 1. And this gives me, what do I have? I have k terms up here, k minus 1 terms up here, so the last term remains. I have n minus k plus 1 divided by, I have k minus 1 terms up here, k terms down here, so only the k remains, and I have p divided by 1 minus p, qk minus 1. So I'm almost there now because I want some a plus b divided by k structure here. And I can get that if I take p divided by 1 minus p, right? Then I notice that here I have n minus k plus 1 divided by k. I can write that as minus k divided by k plus n plus 1 divided by k. So I split up this fraction. And this gives me minus 1 multiplied by p divided by 1 minus p, and then plus p divided by 1 minus p multiplied by n plus 1. All of this divided by k. Parentheses around all of this multiplied by qk minus 1. So what I recognize here is that this thing is my A and this thing is my B. So in conclusion, what we have in this part is that Q0 was equal to, well, the probability of exactly and failures, right? And A is equal to minus P divided by 1 minus P, whereas B is equal to, well, this thing here is just minus A, because I have P divided by 1 minus P, multiplied by N plus 1, where N has to be natural, and based on what I see here, A should be negative, because both P and 1 minus P are positive. However, we have only checked this relation, recurrence relation, for K up until N. What happens if K is greater than or equal to, what happens if K is greater than N? So from K equal to N plus 1, what happens there? Now let's just take a look just to make sure that the recurrence relation is also satisfied there. So Q n plus 1. If we use this recurrence relation, it's A minus A n plus 1 divided by k, which is n plus 1 in this case, multiplied by qn. These two cancel, and then I just have 0 multiplied by qn, which is equal to 0. And this will then imply that qn plus 1 is qn plus 2 is equal to 0, qn plus 3 is equal to 0, and so on until all infinity. So this recurrence relation is indeed something that holds for the binomial distribution, since it actually also allows us to conclude that all k's greater than n have a point probability of 0. So just to sum it all up, let's also draw in here, in the AB region here, in the AB plane, what regions we have for A and B in the binomial case. Well, this is rather interesting because A has to be smaller than 0, right? So I'll just right here, our AB region for the binomial case is all of the points A and B such that A is strictly negative and B has to be written as minus A n plus 1 for some natural n. Wow. Okay, so B is equal to minus n plus 1 multiplied by A. And n is some natural number. So if I look at the line where B is equal to minus A, well, then the AB region of the binomial distribution has to be somewhere here, right? Because all the lines on which the AB region exists, they have a bigger slope than this line. And A has to be negative, so this is B equal to minus 2A, B equal to minus 3A, B equal to minus 4A, and so on and so on. So these lines here, they are the AB region for the binomial distribution.